Good afternoon. So I'm Michela Badioli, he's Achim Woessner, and we're going to talk about how to manipulate light with graphene. Sorry. Where is it? There. Okay, yeah. So, we are PhD students in the Nano-Optoelectronics group at ICFO, that is the Institute of Photonic Sciences at the UPC campus in Casteldefels. What is graphene? Graphene is a single layer of carbon atoms that are arranged in an hexagonal lattice. Graphene was first isolated in 2004 by Kostian Ozelov and Andrei Achim, that in 2010 received the Nobel Prize for Physics for their work on graphene. They obtained graphene through mechanical cleavage of graphite. And what you see in the picture in the center of the screen is graphite that has been mechanically cleaved and deposited onto a substrate. And the darker part is graphite, thicker graphite, and then you see a few layers of graphene, and then the lightest part is actually a single layer of graphene, so a single layer of atoms. Graphene is not only the thinnest material in the world, but it also has many interesting properties. For example, it's the best conductor that we can find, and it has a very broadband light absorption. Furthermore, it is possible to tune its optical and electronical properties by using an electrostatic gating. So let's first consider the picture on the left, where you see the absorption of graphene. Actually, surprising that graphene, being only one atom thick, can absorb 2.3% of the visible light. So this is a huge quantity. And it is also possible to tune this quantity and also the optical, but also the electronic properties of this material in a very simple way. So in the center we can see a sketch of a typical device geometry. So we have the graphene, then we have gold electrodes, and then this graphene is on top of an insulator, and this is on top of highly doped silicon. And basically by simply applying a voltage between the silicon and the graphene, via capacitive coupling, we can change the amount of charge carriers that are present in our graphene flake. And so by doing so, we can change the optical and the electronical properties of the sample. For example, as you can see here, the resistance, we can go from very low resistance to a much higher resistance. For our experiments, we are mainly interested in mid-infrared light. So light that has a wavelength that is on the order of micrometers, which means that it has a longer wavelength than the visible light. This region is used a lot in spectroscopy because it's the region where there is the fingerprint of many molecules. But also it's a very interesting region because it is the region of wavelength at which warm objects emit their thermal radiation. So basically this is interesting for doing thermal imaging and thermal sensing. So this is our main motivation, and in order to investigate the possibility of using graphene for making infrared detectors, we built a setup where we can measure the current that is generated when we shine light, mid-infrared light on top of our graphene sample. So there on the left you can see a typical device where the graphene is in the center, and then you have gold electrodes that are connected with wires to the electronic part of the setup. And then the optical part of the setup, we have an mid-infrared laser, some focusing optics that we use to focus the light onto our sample, and the sample is mounted onto a motorized XY stage, which allow us to make special maps of the sample.
So here we see a typical spatial map of one of our devices. We can do spatial imaging, as Michela already mentioned, using a motorized XYZ stage. And this spatial imaging is only limited by the resolution of the laser we have, which in our case is a resolution of about 10 micrometers, which is determined mainly by the wavelength. So on the right we see a typical photocurrent image which we can reach. So we see two very strong photocurrent spots on the left and on the right, which is exactly at the interface between the graphene and the gold. But there's also other ways to look at the optoelectronic properties of graphene. We can also look into much higher resolution by using near-field imaging, which we cannot do with the laser. So for near-field imaging, we have a conventional atomic force microscopy tip with a tip diameter of about 20 nanometers, which in the end determines our resolution. So we get a much higher resolution than in the photocurrent imaging. So this atomic force microscopy tip is enlightened with infrared light of about 10 micrometers and interacts with this light to create a nanofocus at the tip apex of the AFM tip. This nanofocus then launches so-called plasmons, which are charge oscillations at the surface of the graphene into the graphene, as we can see here. By scanning this tip over the graphene device, we can map out these plasmons in real space and get a high-resolution image of our device, as can be seen here. To do this, we have to look at the scattered light, which is scattered back from the graphene, and detect this. So this is the near-field imaging technique we use for high-resolution imaging of graphene devices. So to wrap this up, we have a short outlook. No, we don't have a short outlook yet, sorry. As I already told you, there is the plasmons are charge oscillations at the surface of the graphene. So as those are oscillations of the charges, and we already told you that we can change the amount of carriers inside of our graphene by simple electrostatic gating. It's quite likely that we can change the intensity of these plasmons. And indeed, we can even turn on and off those plasmons. So for a high charge carrier density, as on the right, we have plasmons, while for a low carrier density, as in the middle, we can turn off those plasmons. So this could eventually be used for optical transistors or optical switches. So now we come to the outlook. First of all, graphene could be used, as Michela already mentioned, for thermal imaging devices to replace current thermal imaging techniques, which are quite expensive. And the other possibility for using graphene could be to use it in optical communication networks as high-speed optical switches or modulators. And with that, I would like to thank you for your attention.